Welcome to this topic, Dynamic Routing Protocols. In this video, we will explore Dynamic Routing Protocol, which are key for efficient data routing in complex networks. Unlike static routing, where routes are fixed and manually updated, dynamic routing protocols adjust automatically to network changes. The flexibility is crucial for large and evolving networks. These protocols let routers share information about the network, updating their routing tables to find the best paths for data. Some common dynamic routing protocols are Routing Information Protocol, OSPF, Open Shortest Path First, EIGRP, Advanced Interior Gateway Routing Protocol, PGP, Border Gateway Protocol. Dynamic routing also helps with network convergence where routers agree on the network layout and routing information, reducing downtime and improving reliability.
What is dynamic routing? Dynamic routing is a method used in computer networks to automatically adjust the paths that data takes from its source to its destination. Unlike static routing, where routers are manually configured and remain fixed until changed by an administrator, dynamic routing allows routers to continuously exchange information and update their routing tables based on the current state of the network. Some of the key factors of dynamic routing are information exchange. Routers share details about the network, including routes and their metric like distance and cost. Routing table updates. Routers update their tables with the latest information to reflect the current network paths. Routers use algorithm to choose the best path for data considering factors like cost and congestion. When the network changes, such as adding a new routers or routers failing, the protocols automatically adjust the routes to fit these changes. Benefits of dynamic routing are automatic adoption. Routers are updated automatically in response to network changes, reducing the need for manual configuration. It handles large and complex networks efficiently by dynamically managing the routing information. It quickly adjusts to network failures or changes, maintaining network reliability and minimizing downtime. Optimized routing, it continuously calculates the best paths for data, considering factors like path cost and network congestion to ensure efficient data transfer. There are several dynamic routing protocols, each designed for different networks. Some of the mostly used dynamic routing protocols are RIP, Routing Information Protocol, a distance vector protocol known for its simplicity and ease of configuration, ideal for small networks. OSPF, Open Shortest Path First, a link state protocol that scales well for large networks by using more sophisticated method of routing calculation. EIGRP, Enhanced Interior Gateway Routing Protocol, a hybrid protocol developed by Cisco combining the best features of distance vector and link state protocols. And the fourth one is PGP, Border Gateway Protocol, the protocol used to exchange routing information between different autonomous systems and the internet.
Routing Information Protocol is one of the simplest and oldest distance vector routing protocols used in computer networks. It calculates routes based on of the number of routers data processed between the source and destination. Here is a breakdown of its key features. Distance vector protocol. RIP uses the hop count as the routing metric, where each hop between router is counted as a unit of distance. The maximum number of hops allowed for a route is 50, which limit RIPs used to smaller networks. If a route exceeds 15 hops, it is considered unreachable. Routers running a RIP send their routing tables to neighboring routers every 30 seconds, updating routes regularly but potentially causing delays in larger networks. RIP is easily to configure and well suited for small networks where minimum administrative effort is needed. There are two versions of the RIP version 1 and RIP version 2. RIP version 1 supports classical routing, no support for subnet mask. RIP version 2 supports classless routing, supports subnet mask, and adds features like authentication for more secure routing. The RIP version 1 is the original version of the routing information protocol, a distance vector routing protocol used to determine the best path for data within a network based on the hop count. Here are its key characteristics. Classical routing. RIP version 1 does not support subnetting or variable length subnet masks. It only works with classical IP address, which limits flexibility in addressing. It uses hop-count metric to determine the best path with maximum mark 15 hops. Any route with a hop count of 16 is considered unreachable. RIP version 1 sends the entire routing table to all its neighbors every 30 seconds via network broadcast. This can cause unnecessary traffic in larger networks. RIP version 1 lacks any built-in authentication mechanism, making it vulnerable to malicious updates or incorrect routing information. And finally, due to the hop limit of the and lack of support for subnetting, RIP version 1 is quoted for smaller, less complex networks. Some of the drawbacks of RIP version 1 are RIP version 1 does not carry subnet mask information in its subnets, meaning it cannot support VLSM, leading to inefficient use of IPFS. Regular broadcasting of those updates increases network traffic, particularly in large networks. Lacks any authentication features, making it vulnerable to attacks or unauthorized routing updates. Retro version 2 is an enhanced version of RIP version 1, addressing several limitations of the original protocol. It remains a distance vector protocol but includes additional features to support modern networking needs. Some of the key features of RIP version 2 are classless routing. Unlike RIP version 1, RIP version 2 supports classless indeterminate routing and variable length subnet masks. Like RIP version 1, RIP version 2 uses the hop count as a metric with a maximum hop limit of 50. Instead of broadcasting updates to all devices, RIP version 2 uses multicasting to send routing updates only to routers, reducing unnecessary network traffic. RIP version 2 includes built-in support for authentication, allowing users to verify the validity of routing updates, providing more security compared to the RIP version 1. RIP version 2 includes next hop address in the routing updates, enabling more efficient routing decisions by identifying the next router in the path. This version to library version 1 sends routing updates every 30 seconds. However, its multicast updates and authentication features make it more suitable for larger networks. Some of the drawbacks of RIP version 2 are limited scalability. Despite the improvements, the maximum of bug 15 still limit RIP version 2 effectiveness in large networks. Like the RIP version 1, RIP version 2 can take time to converge, which may cause routing inefficiencies during network changes. OSPF is a widely used solid-state protocol designed for large and complex networks. Unlike digital sector protocols like RIP, OSPF calculates the shortest path for data using the digital algorithm, taking into account various metrics like bandwidth, delay, and cost, not just hop count. OSPF is a more scalable and efficient solution for dynamic routing. Some of the key features of OSPF routing protocols are OSPF maintains a complete map of the network topology by exchanging link state advertisements with neighboring routers. OSPF supports a hierarchical structure with the areas to optimize performance and limit the size of the routing tables. The network is divided into different areas, with the area 0 being central and other areas connected to it. OSPF uses a digital algorithm, shortest path first algorithm, to calculate the most efficient path based on the cost metrics, which are typically related to the bandwidth of the links. The routing metric in OSPF is based on the cost, which is inversely proportional to the bandwidth. The lower the cost, the more preferred the route. Higher bandwidth links are assigned lower costs, making them more likely to be selected. OSPF sends multicast updates for all OSP routers, reducing unnecessary traffic compared to broadcasting. Support for CIDR and BLSM. OSPF supports classless interdomain routing and variable length subnet masking, allowing more efficient IP address allocation and subnetting. Some of the drawbacks of OSPFs are complexity. OSPF is more complex to configure and manage compared to similar protocols like RIP. OSPF maintaining a complete network topology database can consume more memory and CPU resources and routers, especially in large networks. Border Gateway Protocol or BGP is used to exchange routing information between different autonomous systems on the Internet. It is a crucial part of how the global Internet operates, enabling data to find the most efficient path between source and destination. Some of the key features of Border Gateway protocols are unlike protocols like OSPF or RIP, which operate within a single autonomous system, PGP is used to exchange routing information between autonomous systems. This makes PGP crucial for the functioning of the Internet. PGP is a path vector protocol, which means it maintains the path that data takes to reach its destination. PGP allows for extensive control over routing policies, enabling network administrators to configure how traffic should enter and exit their autonomous systems. PGP, designed to scale well for large networks like the Internet, it can handle thousands of routes, making it suitable for large-scale global networks. PGP uses TCP for reliable communication between routers. This ensures that the router updates are transmitted securely and accurately. And finally, instead of sending the entire routing table periodically, PGP only sends updates when there is a change in the network. This reduces bandwidth usage and allows for more efficient operation. Border Gateway Protocol is categorized into two main types: external PGP and internal PGP. The first one, external PGP, it facilitates the exchange of routing information between routers in different autonomous systems. It predominantly used across the internet to connect various networks, ensuring efficient data travel between independent systems. It operates between autonomous systems, making it suitable for inter-domain routing. It enables network administrators to implement policy-based routing, influencing how traffic enters and exits their networks. The second one is internal PGP. It manages the exchanging of routing information within the autonomous systems. It utilized with large organization to maintain consistent routing information across multiple routers, ensuring efficient internal data flow. It operates within a single autonomous system, providing central control over internal routing policies. It helps in maintaining a unified view of the network's topology among all routers in the autonomous system. Border gateway routing protocols perform three main functions: initial peer acquisition and authentication, and the second one is exchange of reachability information, and third one is about session and network verification. The first one, initial peer acquisition and the authentication. PGP peers initiate TCP connection to establish communication. The process involves handshake and verification to ensure both peers are prepared to exchange routing information. Peers may use authentication mechanism to verify that they are communicating with legitimate and authorized routers, enhancing security of the session. Peers share information about available routes and network paths. This includes updates on new routes that can be used to reach various destinations. Negative reachability. Peers also communicate about route withdrawals or failures, informing each other about routes that are no longer available or valid. And next one, session monitoring. PGP continuously checks that the TCP session with its peers is active and stable. This includes sending keep alive messages to confirm that the peer is still reachable. BGP ensures that the network paths and the connection between peers are functioning correctly. This helps maintain the reliability and stability of the routing process. These functions are crucial for maintaining accurate and reliable routing information across different autonomous systems on the internet. Thank you for watching.